Oh, yeah. I'm sure you guys want to stay longer today. Okay, so yeah, we talked about the different areas of research. So now I talked about the past, I talked about the future, and now I'm going to talk about the present. So this is going to be a look at what you think about when you're actually looking at wind plant design today. So I'm going to go through kind of the typical steps at a very basic level for wind plant design and the considerations of wind plant design, and talk about how you do some layout optimization. And then we'll actually get to showing some example research. All right, so design of a wind plant is challenging. We already, we've covered a lot of that. Just recently looking at all the different coupling of the physics and all this. You have harsh operating environments. These are the largest rotating machines on Earth and getting bigger every year. So huge machines. We're trying to put them in all different areas. Flat plains, which are easier. Offshore, which is very hard. Mountainous areas. So getting these huge, tall machines out to where they need to be, ensuring that they survive the environmental conditions that they're exposed to when they're at the site, making sure that they produce energy reliably all the time. These are all things that make wind plant design very hard and an interesting research problem. So first you're going to start with site prospecting. So what do you guys think that involves? What is site prospecting really about? It's about wind, absolutely. We need to have wind. So you're not going to go build in a site before you know what the wind resource is like. And so the very first step in actually building a wind plant is starting to try and figure out what the wind resource in that site is like. So to identify potential wind farms that are worthy of investment in data collection, which is the first step in the process, you're going to do some modeling and look at potential leasing. And so these are all sorts of issues that you face when you're looking at developing the plant. So the wind resource is key. Also, do you have access to transmission? Are you going to have to build a huge long interconnection line to get to the nearest transmission interconnect? Do you have sensitive environmental and wildlife issues that you might have to deal with that are going to make permitting your plant very difficult? The permitting process itself, local zoning, all these things can influence a project's viability and leasing the land. So we're going to look at all these different things. So the wind resource. The wind resource varies. It varies globally. It varies regionally. It varies over different types of terrain. It varies over land and on water. So at the bottom here you can see a mesoscale map. I think this is 80 meters height showing the wind resource, both onshore and offshore. So onshore, the dark red areas are where you have higher resources, and then darker blue are the lower resources. Offshore, where you have the deep, darker regions, is where you have high resources. And so in the US, we have a huge amount of wind right in the middle of the country, which, no surprise, is right where our highest winds are. In Brazil, I don't have a Brazilian wind map here, but most of your high wind onshore resources are up in the northeast, right? So that's where a lot of your wind energy is built right now. So you look at the wind resource, mesoscale maps are readily available, so that gives you some preliminary idea of where resources are good. And so you start to look at those a little bit closer. Another thing that you want to look at is the seasonal variability of the resource. So wind resource varies over the course of a year, over the course of the different seasons, and even over the course of the day. You can have different diurnal profiles where winds can be stronger at night potentially, or during the day, depending on where you are. And so this is a seasonal profile for one particular site. And you can see here in the winter time frame, it's much stronger and weaker in the summer and then higher in the winter. And so this is common for a lot of sites. There'll be seasonal variation. And from what I understand, here in Brazil, the time when your hydro resources are lower is the time when your wind resources are higher, is what I understand. I see some nodding heads. So you look for that type of complementarity of wind with the rest of your energy system. So you look at the site resource and say, okay, I have a good resource, I think, from inspecting the maps in this area. What is my transmission access like? And so you can find transmission maps, and you can see transmission lines all over. So if you want to build a site right here, you're pretty far away from all these nearest transmission lines. Whereas, up here or over here, there's some transmission access. And not only is the transmission built there, but what type of capacity does that transmission have? What other generation is using that capacity of the transmission right now? And is there enough space for your wind farm to actually share that transmission capacity? So you look at transmission access and say you find that, okay, I feel like I have a reasonably close transmission access point for interconnect. And then I've got to consider a myriad of issues related to environmental, potentially aviation, radar, local built environment, buildings, communities for noise, flicker, all sorts of things that may actually affect the permitting process for your project, whether you can actually get the permits to build it. So one thing we get concerned with a lot in the US is radar interference. If you have wind turbines too near, say, a military facility or something like that, they can interfere with radar, which is not good for security and aviation type of sensitivities. Back. Migration corridors. So there are migration corridors for birds, bats, things like that. So you need to be sensitive and make sure you're not building in a primary spot. Or if you do, how do you mitigate against the potential of impacting wildlife in those regions? And then built environments. What type of communities do you have in the area? How are they going to be impacted by these plants? So developers spend a lot of time trying to find all the different potential impacts from these different areas that could limit the ability to build out a project. And when you account for all these different types of limitations for building out of a plant, which is something we investigate at NREL, you find that no matter where you go, you might have to deal with some sort of challenge to building your project. So what this map shows right here is you have underlaid all this gray stuff is the wind resource in the US. So you can kind of see peeking out is that higher wind resource region here, and the different colors that you can see. What's overlaid on top of it is if you have an area with at least one siting challenge, 2 siting challenge, or the darker ones, 3 or more siting challenges. So these siting challenges are exactly these guys here. Could be a transmission interconnect, it could be a permitting issue associated with wildlife or encroaching on communities. And so when you do that, you find that there's very little space within the country where you can build a project without having to deal with some challenge to actually siting the project. And so these are the things that developers have to tackle realistically anytime they build a plant. And oftentimes they can stop a project. So developers have to be very proactive to making sure they're addressing these types of challenges. Questions on that?
Actually, I'm wondering how do you, let's say, find those maps, those restriction maps in US? Because in Brazil, I use it to, I worked for a company that we developed some wind farms here in Brazil. And it was actually really hard to get every piece of information which is really broken. So
yeah, so we have an entire research group that's dedicated to looking into this. And so they've, over the years, aggregated a lot of data in the US from a myriad of sources from the federal government and different agencies to try and synthesize and bring all this information together and develop these maps to support developers in the US. But it is very difficult information to access, and oftentimes we're doing it through grants and research projects and things like that. Okay, so land leases, sorry, one more, need to get the land. So, you know, you found a good resource site, you think you can permit it easily, or at least, you know, without too much, without it getting roadblocked. Then you have to get landowners typically to sign a lease for their land. And so oftentimes you're not going to get a nice comprehensive circle or square, you're going to have a patchwork of leases that you get in a particular area, and then you have to decide how can I fill in my wind farm in these land leases that I have available to me. And so that just in and of itself, without getting into any of the optimization, is a difficult process in terms of how to design a wind plant. So from there, okay, now we have our general site. We think this area is good. We've got some leases to go, but we don't trust the mesoscale maps. Typically, the mesoscale maps are a very rough idea of what the actual wind resource is going to be at a particular site. So you're going to actually collect data at the site to try and actually prove that you have a good resource there. You're not going to just trust your mesoscale maps. So what is resource assessment? It's estimating the long term, because we really want this plan to be successful and profitable over the long term, probability distribution of the wind resource at a site in terms of both wind speed and direction. How many of you guys know what a windrose is? Okay, a good number of you. You'll see a couple. You'll see some in a second, but just to get a gauge on your guys' background. And so, yeah, we're trying to characterize the long-term performance, potential performance of the wind resource at this site. So why do we care about that? Why do we care so much about characterizing the wind speed at the site? Well, yeah, money, of course, but like from a scientific perspective, why do we care so much about characterizing the wind speed? The performance, and why the performance? Why does the speed matter to the performance? The velocity is related, and how? Anyone remember from earlier? Cubed, right? Yeah, exactly. So power from the wind is a function of the velocity cubed. So this probably potentially matters more than any other parameter up here in terms of actually determining how well your plan's going to perform. So we want to be able to ensure that we have a really good characterization of what that long-term wind speed is going to be at the site. And by doing so, we can reduce debt financing costs, lower uncertainty in what we actually get out of our power production, and ensure that we have a good performing plant long-term. And how do we get that? Any ideas how we get this long-term estimation? Sorry? Measurements. So you try to collect at the plant actual data and measurements. Typically, you'd like at least a year of data at a site, at minimum. Most places you'll want at least 2 or more at where you're going to have nearby to representative turbine locations. And so you actually go out and you measure the wind speed and direction at the site. And then you're going to try and calculate from that and estimate what the long-term profile of the wind speed and direction is. So we do that typically with met towers. Historically, met towers have been the bread and butter of the resource assessment industry for wind. You have towers typically ranging from like 60 to 80 meters. You can tilt them up or have them on lattices. And they'll be instrumented up and down with a number of sensors, right? So you'll have these anemometers, wind vanes, sometimes sonic anemometers, temperature sensors, sometimes barometric sensors. So all sorts of ranges of different types of sensors that you can use to help characterize the wind profile at that site. And so you put this up close to where you think you're going to put turbines, and you measure those sensors for, as I said, hopefully a year or more. And then you're trying to characterize from that longer term potential. So met towers we also use SODARs and LIDARs. I spoke earlier to those. These are newer. They're much more expensive, but they've come down in cost. It used to be that one of these guys would be a couple hundred to more thousands of US dollars. They're now down to, like, you can get one near down to sort of the 50K mark, 50,000 US dollars. They're still expensive, much more expensive than met towers, but they do provide that more higher resolution profile of the wind speed and more information about the wind speed over time. So they are useful, and more people are starting to use these, often in collaboration with the met tower. So they'll have a met tower plus a LIDAR. They'll use the met tower as sort of a calibration or a validation of the LIDAR measurements, and then they'll use those together to get wind resource information. And then from there, we look to projecting forward what our long-term potential is. So we've only got 2 years of data, and what if the wind varies? What if we just had a really good 2 years? And then, or what if we had a really bad 2 years? Climate is changing constantly, and you'll have periods or years of really good performance and really bad performance. And so if you measure for 1 year or 2 years even, you're not getting a really good estimation of what the long-term resource is at the site. So the way we do that then to actually take that data and project it to that long-term trend is compare that data to reference sites which have been around for a lot longer, hopefully more than one. So here you can see we have our target site where we have just a limited set of data, and a reference site where we have hopefully 10 or more years of data. Typically you want 10 or more years of data from your reference site. Anyone know where you might get those reference site data from? Airports. Airports are a great source of referenced site data. Most airports around the world have been collecting wind speed and direction information, albeit lower to the ground than we'd like, but for very long periods of time. What other sources of data? If you're a developer, say. Sorry? Reanalysis data? Sure, from other sources of larger meteorological campaigns and things like that. I was thinking more like if you were a developer. Other plants, right. So sometimes you'll use, if you have a plant that's not too far away from like a plant where you're going to build, you might use the data from that plant. So there's all sorts of different sources of reference data that you might use to actually use as comparative sites. So you take your longer term profile and your shorter term profile, and you essentially do a comparison of the two. And you try to build statistics that show the correlation of the statistics for your target site and the longer term reference site. So you can see here is a little model where you have this sort of data training, testing, learning algorithm, evaluation, and this sort of what we call measure, correlate, predict. So we measure from the site, we correlate it with another site, and then we predict forward what that long-term characteristic resource is going to be for our site. And so you do this in a lot of different ways. People are getting much, much more sophisticated about how we do this. This is one area where data science comes into play. You can use all sorts of different ways to correlate the data. You can use a simple linear regression, matrix methods. People are starting to look at all sorts of neural networks, different types of machine learning, and you can get really sophisticated in how you do this process using different mathematical techniques. So one big area where data science is definitely useful for wind energy. And then you determine your sort of historical distribution for wind speed and direction at the site. So here's your sort of reference site wind speed, your site wind speed, and shows the joint probability distribution of the two. So you've done that, you've created this sort of relationship of the two together, and so from that you sort of project what is your long-term resource at this site, and you get something that looks like this. These are wind roses, and I just pulled a random selection of these off the web. They vary a lot for all over the world. Different sites have very different looking wind roses. These don't look anything alike, do they? No, not really. No, they, you have this one here, which has sort of a bimodal distribution. You have a really strong prominent direction from the north, and then sort of a second mode here coming from the west. And so what these colors represent on the wind roses are frequencies of different wind speed. And then these are different direction bins. So essentially what this shows you is a joint probability distribution of the speed and direction at your site on a polar plot. And so you can see here, this is a pretty uniform distribution. It's somewhat bimodal. You have a somewhat prominent direction to the southwest and to the northeast, but kind of uniform overall. This one has relatively uniform direction from the south. This one has a strongly directional dependency from the south, but then some uniformity around here. And so every site will have a very different looking distribution. They may be similar if they're all in the same region of the country. So for instance, in the interior of the US, I know that most of the prominent winds are coming from the northwest and the southeast because that's just the general profile for that region of the country. But there is a lot of, depending on the topography and other things, there's a lot of variation in how these might look for a particular site, and your resource assessment will tell you how that looks. Questions on this?
For a project developer, which wind profile is more interesting from these 4 cases?
We could ask the project developer over there. So let's see, which would I think is the most interesting? Because when I see this in my mind, I start to think out is layout optimization. So how do I optimally arrange my wind turbines is very much dependent on this wind rose. And so for me, I think that the bimodal one in this right corner is going to be an interesting one from an optimization perspective. But from a developer's perspective, I don't know, do you have a thought about that? Yeah. Oh, you agree. He also agrees, okay. But maybe not for the same reason, I know, but you're thinking.
Actually, I come from the northeast, and there it's really easy because we just have almost omnidirectional wind. So within, let's say, 60 degrees, we have 90% of the wind coming all over the year. So just coming from one direction.
Oh, yes. I'm just wondering, this is very nice, this way, the distribution, because you can see the direction as well. That's very interesting. I'm just wondering, some people use, you said that the probability density, some people use the Weibull. I don't know how does it fit, but that's one direction, I believe.
So that's a great question. I'm going to get to that in just a second here. Yeah,
all right.
Yeah, so this gives you sort of that windrows, that joint probability distribution of direction and speed. So yeah, I'll get to the Weibull in a second. Just one more thing on these resource assessment. You can have long-term variation that even goes beyond 10 years, 5 to 10 years. You have these long-term climatological trends, and those can affect your long-term resource. So there's intra-annual variation in your wind resource, and so that's a much more sort of advanced feature of resource assessment that people who are doing this in practice try to investigate and correct for. And the way they do this typically is they add uncertainty to their resource estimate to account for this inter-annual variation that's somewhat, I would say, very difficult to quantify accurately. And that also varies spatially. So how much intra-annual variability that you have in different time periods will vary depending on your location in the world. And again, because power is dependent on the wind speed cube, these variations in wind speed have huge impacts on the potential performance of your wind farm. So you want to try to characterize it and explicitly characterize the uncertainty around it as well as you can. So that's data collection. I'm going to get next to wind flow modeling. So wind flow modeling now is we have this resource, that's for the whole plant in terms of an actual resource. What do we think we're actually going to get in terms of energy production out of the plant? So motivation. Given what we know about the data from on the resource from our met mass, what do we think we can actually get from the turbines at specific locations in a farm? So if we have a met mass here and a turbine over here, and we characterize our long-term resource here, will it hold at this turbine location here? So wind flow models will help us translate our met measurements to where our actual turbines are. The other things that they do is they account for the wake effects in the flow. So we talked about wakes earlier. Wakes obviously have a huge impact on your overall plant performance. And so these wind flow models help you characterize what is the actual resource at where my turbine is going to be located, and given the other turbines in the plant and the waking from different directions, how much energy will that turbine and the whole plant produce over the course of the year? And that's what wind flow plant modeling is about. And there's different resolution of models we can do with that. So they range from purely statistical, numerical weather prediction models, all the way to CFD, LES, coupled with an aeroelastic code, fancy, like, Rolls-Royce of models for, wind plant modeling. And all these things are used for research, but in practice, typically what we use for wind flow models for parks are these linear flow models. So these linearized Navier-Stokes models. And we use those to actually design and estimate the power production for a plant. But you do have a whole myriad of them. And most of these NREL works on, and we have developed open source versions of these codes that you can use for research as well. And so I'll speak to that a little later. I had a few questions on that earlier. Okay, so linear flow models, primary engineering analysis tool for wind farm layout design. They're linearized the Navier-Stokes equation for neutral boundary layer conditions. That's important because in real plants, oftentimes you're not in a neutral boundary layer condition. You can have stable or unstable conditions, and those impact your wind energy performance. That's an active area of research. Essentially what they do is you calculate speedups due to obstacles in the plants in different locations by assuming this sort of superimposition of individual hills. So you superimpose these individual hills that represent different obstacles in the plant, and you get this sort of speed up map where wind speed varies over the terrain. And so then you use your Met Tower data to sort of calibrate what the velocity resource is at every site in the park using that sort of speed up effect. It breaks down under a number of conditions, so there's flaws to these model. If you have steep terrain, mountains, ridges, anything like that, these models don't work well. I just mentioned the atmospheric stability, so if you don't have neutral stability or in stable or unstable conditions, they also don't work very well. They don't capture intraplant speed-up effects, so you can have speed-up within your plant depending on the placement of the turbines. They affect the flow, and so that's not captured. And there are other things as well. So the models are not perfect, but they are good at giving you a first-order approximation and estimate of what your wind energy production is going to be at a plant. And they've been heavily calibrated over the years. So we use, again, data assimilation, taking information from higher fidelity models or real world data, and use those to calibrate and inform these models and make them more accurate and closer to reality. So there's different types of linear flow models that have been developed over the years. You can find numerous publications on all of these. The Park model is the oldest and probably the most used. It's sort of this trapezoidal velocity effect, which has this sort of velocity that the deficit of the velocity, which is here, sort of decays over time and expands and eventually goes away. You have this eddy viscosity model, which is closer approximation to a time averaged LES simulation. So different flavors of these models over time, a wide variety of them that you can use. All very sort of computationally efficient is the key, because if you're using them in design optimization, they need to be computationally efficient. Here's a Park model. This is, I think, maybe the only equation I have in my presentation. I wanted to keep things light for the end of the day. So it basically shows that you have the velocity of a wake at a given position downstream is dependent on the upstream velocity, the axial induction factor, the diameter of the rotor, the position downstream that you're calculating things at, and then the surface roughness factor K. And so what's interesting about this, what does this tell me about sort of wind plant design, is that these wakes and the losses in energy production associated with these wakes are dependent on the size of my turbine. So as my turbine sizes change, the effects that they have in terms of wakes on other turbines change. It's dependent on the operational state of the turbine, right? So the higher the axial induction factor, the more you're going to have in that deficit. So that's also going to be a factor. So you're going to want to place turbines farther apart to account for that. X, relative position of the turbines. So I can reduce the effects of these wakes by moving the turbines farther apart, and again, reducing the wake losses. And they depend on the site characteristics. So particular local topography and the surface roughness based on the topography will actually impact the wake propagation through the plant. So all these things factor into the model, and so that's what we need to account of in combination with the flow model to understand what our actual energy production from the plant will be. All right, so I am going to move on now to wind plant layout optimization, which is where we actually, rubber meets the road. We use these flow models, our resource assessment information, and actually start to look at wind plant design. All right, so the general process for this is we take our overall available land area that we have with leases and everything, we subtract out the infeasible region. We call those typically exclusion zones in the optimization world. We take our measurements, we do our MCP and flow models to establish a wind resource grid, that's that speed up map throughout the site. Then we're going to perform an optimization. And so this optimization is going to actively model the energy production over time as we change turbine positions, accounting for the probability, that probability distribution of the wind rows of the direction and speed coming into the plant, as well as the losses. So, from a simple perspective, if you have sort of a uniform direction, or say I'll show you visually. I think it's too hard to explain with my hands. Not very good at creating wind park with my arms. All right, so what we want to do is maximize the energy capture, gross energy production, and minimize those wake losses that would be leading to the net energy production. Minimize overall costs. Those are typically our infrastructure costs for roads, electrical cables. And sometimes you'll have a fixed or a variable number of turbines. So sometimes the actual number of turbines in your plant is one of the variables in the optimization process. Then once we've established this layout, we're going to look and make sure from a site suitability standpoint that the turbines can actually withstand the loads at the particular location where they're going to be placed, and adjust turbine locations if we need to. And more recently, there's a lot of work using higher fidelity simulation tools to actually, after you've done layout optimization, to actually assess in higher fidelity tools what you think the actual energy production. So using some of those higher fidelity models I mentioned before. All right, so tools for MCP. This is mostly kind of, you know, a resource information for you guys. If you're interested in looking at tools for doing MCP and resource assessment for a different wind site, WASP is one of the oldest. It's out of DTU Wind Energy in Denmark. I think they have a student license version that you can get, I believe you can get access to. That's either cheap or maybe free, I'm not sure. Don't quote me on that. My DTU colleagues will come after me. Windographer is out of WindLogix and is also a great tool for doing MCP. Wind Navigator from AWS True Power. I talked to one student here today that's using that one already. So these are all good tools for doing MCP that are used in commercial practice. You can see sort of the WASP process here. You take your sort of observed climatological conditions and propagate those up to a general wind climate and then back down to your site. So that's just sort of their illustration of the MCP process. And then here's where we get to the Weibull. If we were looking at from a single turbine, going back, let's forget the plant for a second and going back to our single wind turbine, our annual energy production essentially, we've seen this plot already today, it's the convolution of our power curve for the turbine with our Weibull distribution of the resource, right? So if we just did the frequency distribution of the resource, wind resource for the site, you know, leaving outside the direction dimension of things, then typically it looks something like a Raleigh or a Weibull distribution, this blue curve here. And then we have our power curve here, and so when you convolve those two together, you get sort of the energy production at these different bins. And so then you can add and integrate those up, and you get what your annual energy production will be for the turbine. Capacity factor then is that actual energy produced based on the Weibull distribution you have for the site, divided by the power production if the turbine were operating at rated, be 100% of the year. So the higher capacity factor essentially, it's a proxy for how often the turbine is operating at its rated power. And so capacity factors for thermal plants are traditionally much higher, and so that's something that wind energy has been chasing over time, is to try and boost that capacity factor so it can look more like a conventional thermal plant. And we're getting there through doing a number of things, getting to higher and higher capacity factors. It used to be that 30% were like a good plant, 30 to 40%. Now we're seeing capacity factors of 50%, upwards of 60%. So we're getting better as an industry, looking at optimizing not just for cost of energy, but getting those capacity factors for supporting the grid up. So that's a single turbine perspective. Of course, you know, turbines of plant, as we've talked about many a time today, suffer from wake losses, and so our actual capacity factor is going to be less than this, primarily because of wake losses. There are other losses in the plant. You have electrical losses, you have availability losses because turbines are down for maintenance. There are many losses that factor into the plant, but the dominant one affecting your, going from your gross energy production that you could get out of this to your net energy production of what you actually get is your wake losses. And so optimization of your weight of your plant is really mostly targeting at minimizing these losses for maximum net energy production, also while minimizing costs. So pause here for a moment. Any questions right now? Okay. All right. So now to the design process. Wind plant optimization is complex. How many of you guys have taken a class, have some background in optimization? Okay, some. If I say gradient-based optimization, who knows what I'm talking about? Show of hands. Okay, one person. All right. So gradient-based versus gradient-free are different types of optimization techniques. But basically what I'll get to is wind systems are great for doing optimization research because they are really hard optimization problems. So there's lots of variables. You have turbine in a plant, turbine X and Y positions at a minimum. You may have a whole number of other design variables. Maybe, like I talked about earlier with the student, you might be placing your substation, so the location of the substation, all of your electrical cabling, its topology, where you're building your roads. All these things can be design variables, so that's a huge, huge set of design variables. Many constraints. setbacks, exclusion zones, turbine spacings. And these constraints are not nice. Sometimes you'll have an exclusion zone in the middle of the plant. That's really hard for an optimizer to deal with. I won't get into why today, but if you're curious, ask me later. Discrete variables. Discrete variables are not fun for optimizers, not fun at all. And turbine number is often included in wind plant layout optimization processes. Attributes of the turbine. You may have different designs of turbines, different hub heights. Those all make optimization very difficult. Discontinuant functions. You have cost functions of infrastructure that may have step changes. These things are not fun for optimization. Uncertainty. Very not fun for optimization. So resource, your resource itself has uncertainty. Costs have uncertainty on O&M and other things. So all these things make optimization of wind plants really, really tough. And optimization is a huge field. And again, sorry the fuzziness here, but basically there's all sorts of different ways you can slice and dice optimization methodologies based on problem features, types of methodologies. A lot of times people try to break them down in hierarchies. I'm never satisfied with what they come up with. I like more of sort of a Venn diagram approach, but it's very complex. There's all sorts of different techniques you can use and tied to the different problems you're dealing with, but you know, just boil it down to wind plant optimization is hard. So we try to make it easier. We try to sort of, make continuous variables out of discrete variables. We try to reduce constraints. We try to, eliminate unfriendly constraints and discontinuities. We try to reduce the number of variables, do sub-optimizations. We try to do a lot of things to make this a tractable problem. And then what that gets to is a lot of research in wind plant optimization. So this plot sort of shows the growth in this field over the last several years. It only goes through 2014. The trend essentially continues since then. A huge amount of growing research in the area of doing wind plant optimization. So you can see sort of just picking up in the mid-2000s and growing. Objective functions, oftentimes historically people were doing AEP with cost constraints. So a minimum and maximum spacing between the turbines, exclusion areas, et cetera. And that's a lot easier. Just dealing with an objective function of AEP is a lot easier than actually having the cost function in there for your models as well for infrastructure and all that. However, it's not really realistic. So what we've seen more recently is full cost of energy optimization for wind plant layout design. So tools like OpenWind, et cetera, which I'll get to in a moment, actually do optimization at the cost of energy level, because the types of designs you get when you just maximize the AEP of your site tend to be unrealistic, not what you would build in practice. So that's kind of the trend in the research space. Here's a bunch of different tools that you can use for doing wind plant optimization. So we have our sort of suite of tools at NREL that are all available open source. DTU Topform, also open source. So these are open source tools that you can pick up, download, and play with today. They are less user friendly, so they definitely have a learning curve to use them. Commercial tools are much easier to use, but often are licensed. OpenWind is becoming an industry standard, especially I would say in the US and other places as well, for doing wind plant layout optimization. There's an open source version of it I think some of you are already using. And that's a great tool set. They have some great tutorials, and it really helps you think through what it is like to actually design a real wind plant. Other big ones in the industry are DNV GL Wind Farmer. That one's been around for decades. WindSim and WindPro. So these tools are all used in industry for doing actual wind plant design and go through the process essentially of, you get your sort of GIS data, your resource data, start with an initial layout, and turbines will move around, and eventually you'll get to some sort of optimum layout. So that's on the tools. Any questions on that? Okay. All right. Yeah, so here's kind of an example of a typical process that's used by a lot of these commercial tools for doing their optimization. It's sort of what we would classify as a heuristic algorithm, a greedy heuristic algorithm. So they maybe start with a random layout and move the turbines into non-excluded areas. And then they'll iterate over energy capture or cost of energy, depending on the objective function. They'll attempt to find positions for each of the turbines, a new position. If when they change that turbine position, energy capture goes up, they keep it, otherwise they'll throw it out. And then they'll do that with all the turbines in the park. and they'll keep perturbing the turbines. So once all the turbines have moved, then they'll do a full energy capture for all the turbines. If the total energy capture is better, then they'll keep it. Otherwise, they'll return the turbines to last position and try that iteration process again. Yeah, then they'll rerun energy capture, check for improvement, and if it's less than the energy capture before, they move all the turbines to the last position they were in. So I have a video here, but I think I'm not going to show it in time because it's a little bit of a long video. But this is in the slides, and it's also on the Open Wind, tutorial page. They have a lot of videos and tutorials which give a nice overview of doing wind plant optimization in practice. All right, so as I said, once we actually think we have a good design in terms of energy production, then we move on to loads analysis. So Dr. Gao spent a lot of time this morning looking at kind of the dynamics and loads for turbines, especially for offshore applications. So turbines are designed to these standards, IEC 61400-1 and -3 for offshore. One question, who has heard of the IEC standards for wind turbine design? Okay, so all turbines have to be certified to the IEC 61400- series. So they're very important in design.
Thanks. My question is about the wake losses. So I was just wondering if you cannot play like with the position of the turbines, like maybe 1 meter like right and left, or maybe having turbines with different heights, like maybe this one is 1 or 2 meters like shorter than the others, or if it's going to change too much, like the efficiency because of the optimum position of the wings.
So that is a great question. We've actually done some research looking at that. So there's a few parks out there that have been built with different hub heights, and there are product offerings now where OEMs have moved to basically product platform offering, where you have kind of different combinations of diameters, generators, hub heights, especially hub heights. You'll have a number of them for different types of turbines. And so that begs the questions, can I get better power if I use different combinations of turbine sizes in a given park? And so it depends a lot on the site resource characteristics. And so we didn't talk about the dimension of shear, but there's also sort of that third dimension of shear with your probability distribution where things increase with height, but how much it increases depends very much on the site-specific characteristics. And so how much benefit you can get from having multiple heights depends very much on that shear. And so I have a paper or two I could send you which actually investigates that specific problem. Okay, so back to loading for the turbine. So yeah, here's an example loads table that you get from running some design load cases from the IEC. So that is what the turbine is designed to, this standard. And standards sort of, and there are variations of the standards. Turbines manufacturers sometimes have their own class S version of the standard, which is a slightly different type of wind resource that it's designed to, but they're still sort of not site specific. Once you get to a specific site, things change. So real conditions depend on the resource at the site, which will be different from the type of resource that the standard is aligned with. The specific location within the plant, so the terrain, the canopy, forested areas, and nearby extractions that can affect the local resource of the turbine. And then the location of the turbine relative to the other turbines. So wakes not only impact power production, they actually impact as well the loading of turbines one to another. So partial waking in particular is bad for turbines because then you get this asymmetric loads profile where wind on one side of the rotor plane is higher than the other, and so that can be bad for wind turbine loading. So real conditions depend on this, and so you have to assess how will this turbine actually do when it's placed in that specific location amongst all the other turbines in the plant. And so there's another standard, IEC 61400-15, which is actually looking at site suitability. And so you're looking for all your turbines in the site and evaluating whether they can withstand the particular characteristics of the environment and their position in the plant for that site. So that's the next step in the process. And so a question then is, so which of these turbines will experience the highest loads in operation? Let's say this is all the same wind resource site, but they just have different sorts of topography and layout characteristics there. So which do you think will be the highest loaded turbines? Anyone want to shout it out? Shout a guess out. There's no right answer. I didn't do analysis on this. This is just, you know, informational. Anyone want to hypothesize? The middle? This guy? Yeah, that could be. So one thing that could be a significant loading issue here might be that you have sort of, when you have a land to sea interface, complex things happen with the flow in those environments, and you can get all sorts of interesting things like inversion and other stuff, which can create interesting types of loading conditions. So it would be important to evaluate what type of effects being in a coastal environment has on the loadings of those turbines at that site. Others? Which one? This one? I thought that was crazy. I had to actually look up and ask myself, I was like, is this a real wind plant? Like, I couldn't believe it. I was like, I can't believe they actually build a plant like that. And it is. It's a plant, I guess, somewhere in Vermont or something. I don't know. And, you know, it's hard to tell how far apart these turbines are here. Obviously, the wind direction must be coming across like this because the spacing between the turbines this way is super tight. So it's this ridge-type environment. But ridges are crazy weird in terms of creating, you know, speed-up effects and all sorts of updrafts and other types of flow conditions that might be harmful to the turbines. So if you're going to put turbines here, you know, you can optimize them for energy capture, but you better be sure that they can withstand the loads at that site, huh? Okay, any others? Okay, quick answer, all of them are interesting. So this one, of course, wakes offshore tend to propagate much longer than wakes onshore, just because of the smoothness of the ocean surface. And so you're going to have all sorts of partial waking in offshore plants, which can be hazardous to your turbines, and you want to evaluate how often and how much they're experiencing that partial waking effect. Up here, this is the nicest one. You know, this is flat terrain. Maybe it's in the middle of the US somewhere. I don't know, cornfields, et cetera. It looks pretty nice. But you never know. Out in the middle of the US, we have this thing called low-level jets, where we have this super fast, high-moving air that comes very low to the earth and can pass right through the rotor plane and be nasty. So you want to do some analysis for that. Hills, even shallow hills can create some loading effects too. So these are all things that we need to take care of and look at from a site suitability perspective. But if I had to guess, I'd say I think this one is probably going to experience the nastiest loads. That's just my guess. All right, wind farm construction, last piece. And so this will be really quick, but just to kind of share with you guys what actual wind farm construction entails. These are huge civil engineering projects. So, you know, we got through all the mechanical engineering, the aerodynamics, the structural dynamics, the controls, the electrical engineering, you know, mid-ocean, marine, et cetera. Then you get to, you actually have to build these things, and these are huge, huge, huge machines, huge civil engineering projects. So that in and of itself is a big part of the design process. So here you can see construction of the foundation. This is land base. So you have to clear out a lot of land, bring in cranes, you do a big cement pour, you know, put down all this rebar, construct the tower, uses cranes, you construct it in several pieces, you have to bolt it all together at different sections. Rotor, you got to usually assemble the rotor on the ground and then lift it in one piece, although sometimes depending on the plant you might actually install the blades on the turbine after the hubs and nacelle assembly has been lifted. So very complex. So nacelle, yeah, lifting and placing the nacelle. So pictures can do so much for you, but really video will give you sort of the best idea of this process. So I'm going to show you a construction video for one wind farm here. If I can I click on that link? Maybe I can, maybe I can't. Oh, there it goes. Nope. Oh. Can you maximize it to the screen? Or is it not working? There it goes. All right. So this is kind of just getting ready for the foundation here. They're carving out some access road area. So the foundation, which is a concrete pour, about 10 feet deep, 3-4 meters deep. I can't convert to meters in my head very well, so if anyone can shout out the numbers in meters, please go ahead. Yeah. All right, so here come the blades. This is pretty awesome. Has anyone ever seen other videos of rotor wind turbine blades being moved around on different roads and offshore? It's just amazing the things they have to do to get these things to site. They're so huge. The longest blades are getting towards 100-meter long. Land-based ones are between 60 and 70 meters. It's just huge machines. I love when they're showing the blades walking around, the people walking around, because you can tell the people are walking, but it looks like they're running in the video, so you know how slow that these things are moving in actuality. It takes a really long time to get a blade just to go like 100 meters. Okay, so then they're creating the staging area, so they get every piece positioned exactly where they need it positioned before they actually start to assemble anything together. £97,000. How much is that in tons? 50 tons for like a single segment. That's about right. Like 150, 200 tons or more. Upwards 300 tons for a tower. Yeah, I think towers today are typically about 300 tons total. 300 tons of steel. All right, so now they're going to do a ground-based assembly of the hub and rotor assembly here. And one of the things that they have to be careful of in practice is like the loads that the blades can experience during the actual transport and installation can actually be very high. So they have to ensure that when they're transporting and installing the blades, they don't actually put loads on them that are too large for the blades to handle. All right, last tower piece. So I think that was around 300 pounds total. So yeah. Anyone know what turbine manufacturer this is just by looking at the nacelle? Sorry? I think it's a Siemens. I think it's a Siemens. They tend to have that round nacelle. And you can really tell when you look at the hub. They've got that flat hub nose, which is like the characteristic sort of Siemens hub. So Siemens Gamesa now. Now they're going to do a tower climb. So no one here, has anyone here climbed a wind turbine before? A couple people, awesome. So yeah, did you guys take an elevator or did you take climb assist? Elevator? Elevator, so on the one I had on site, we have what's called a climb assist, and they hook a thing to your back that basically takes the weight off. So you still have to climb, but it's like you only weigh 30 pounds or something. So you still get tired because, 80, 90 meters in the air. It's still a lot of stairs to climb. All right, so that's it. That's how you build a wind turbine. So you can see it's a pretty complex process, and there's actually been a lot of refinement and work that's gone in to bring down the costs of the actual installation of the turbines themselves. All right, so that, let's see if I have my mouse back. Maybe. Not yet. But that's the end of this segment here. Then I'm going to go on to talking about some of the research optimization work we do. So questions about wind plant design?
Hello. I just have a suggestion for the organization. I was trying to see the last presentation and I couldn't reproduce the video. So I don't know if we can have access, are your simulation, are your videos, because I find really nice.
Okay, yeah, so the file for my presentation is like 350 megabytes. So it's a big file, but I'll see if we can put it on the Google Drive somehow. I may have to like take out the videos separately or something. I'll see what we can do there.
But
the different simulation videos we have. Yeah. Any other questions about plant design or comments?
But my question is...
You do have a question,
yeah,
okay.
I have a question. It's like, I see you told that like for analyze the data, you took like 2 years, and for make like a construction installation like 3 weeks. Like I think that is not just 2 years and 3 weeks. How long will it take when you say, yes, I'm going to make like a farm wind, until that you already get offshore and onshore?
That's a great question. So yeah, so this is sort of like a overlapping process. So a lot of times developers will have a bunch of Met towers at potential locations at the same time, and they'll be actively developing a subset of sites, right? So they're sort of like rolling through. They're looking at some sites while they're developing others. And so there's like a cascade or a pipeline of projects that are in different stages at one time. But it typically, yeah, you want to measure the site 1 or 2 years. And then the permitting process, 1 to 2 years. Construction usually less than a year. So I've heard anywhere between 3 and 5 years from when you start like doing data collection of a site to actually building a site. But I'd be curious to hear our developer who has the mic over there, his estimation.
Sorry, I didn't get, I was not.
So about 3 to 5 years from like when you put a Met tower to start measuring data to actually building and finishing building a plant?
Yes, actually here in Brazil, you're obliged to measure for 3 years.
3 years?
Yes.
Okay, yeah,
Minimum.
So even a little longer. Oh, that's a good question. Actually, so the numbers I told you are generally sort of my sort of general knowledge for land-based systems. I don't know as much about offshore deployment.
Okay, so I have a question about the yaw control, let's say optimization in order to reduce the wake on the, let's say, downwind turbines. So have you done any kind of analysis about the induced load on the turbine, because it will be misaligned regarding the upcoming wind?
Great question. Yes, we actually did an entire campaign on our GE 1.5 on site and on the Swift turbines in Texas with Sandia. So we've done multiple campaigns now looking on the loads, both from yaw misalignment for doing the wake steering and also on the downstream turbines that are experiencing partial waking. And so there's a lot of interesting, I can send you some papers and presentations on that. You can email me later. But the crux of it is, generally, wake steering is most effective in region 2. So we probably talked this morning about, you have region 2, which is before rated for your wind turbines. This is where wake steering can actually increase power the most. And this is before rated. So your turbines are essentially, at that point, you have lower velocities. And so like you do see some sort of incremental increase in loads. But because you're in region 2, those loads are small. So if you look at it from the whole spectrum of the lifetime loading of the turbine, it's not a significant impact, especially for the angles of steer. It also depends very much on the angles you steer at. And so there's sort of a maximum angle where you sort of maximize the benefit from wake steering, and then it tapers off. So within the steering angles that are good for the maximum benefit, as well as at the speeds that you want to steer at, we basically established that we didn't see significant negative impacts to the loading on the turbine. And so we have some research studies that looked at that. Yeah.
Hi, my name is Ulisses from Brazil. Congratulations for your presentation. And for your experience, could you talk about the main mistakes in the projects in assembly, startup, commissioning?
Mistakes. So I think, you know, I don't have a lot of experience, or, well, any experience at all building wind plants, because I'm a researcher. But I can speak from a kind of one area that has caught the industry in the last decade or so is on the resource assessment side, having a bias in the resource estimation that have come out of the models, you know, from these different commercial codes. And so there's been a lot of work in the last several years to try and analyze like why we're getting a bias between the models and the actual wind site performance, and to correct for that. So there's been a lot of active research to try and address those issues. Another thing that we've seen a lot of in the field is that, you know, there'll be certain turbines that, you know, are expected to perform a certain way, but they significantly underperform, or they have more failures, or, you know, and so it's difficult to figure out why. So a lot of consulting analysis work goes to understand, like, in a particular plant, why do certain turbines perform well, why do others not, you know, why do certain turbines in a plant experience more failures? And by understanding the physics, going back to the earlier part of the presentation, getting into and advancing the physics of wind energy science at the plant level, hopefully we'll be able to, in the future, better understand, you know, why turbines are behaving the way they do when they're in a plant, not just turbines in isolation, but from a whole plant perspective.
During the optimization problem, can you switch the model of the turbine, or you optimize just using one model?
We've done some multi-turbine optimization study. I have in my slides, which I definitely won't get to, definitely won't have time for it today, but at the end of the slides and sort of the advanced case studies, we did sort of a multi-turbine optimization study, and it's there, and we have some other papers there as well. So if you email, I can point you to some papers in that area. Can I do a time check? I just want to know what time it is. 5:30? Okay, all right. Was there any more? Maybe I'll just move on for now, and we'll hold on to more questions. So, all right. Okay, so I'm just going to do a little bit here on some of the optimization work that we do at NREL, looking at wind plant design. We look at both turbine optimization and plant optimization. At the back of this slide deck are examples from our research, both for turbine design optimization and plant design and operations optimization. But I'll just walk through the yaw control example today with time. But we've talked before about how wind plants are very complex and highly coupled systems. These activities, though, are typically separated between, you have your OEMs, your component suppliers, your developers, your owner-operators, all different stakeholders. And so when you look at things from a whole system level, we could improve things a lot if we did design in a much more integrated way. So the fact that all these activities are spread across stakeholders, we have suboptimal, often, system-level performance and costs. And also risk aversion to the adoption of new innovations, because no single stakeholder wants to take on the whole risk of an adoption of innovations. So we've seen this equation already today a number of times, and hopefully over the last several days. LCOE, we often sort of characterize system-level performance and cost in terms of LCOE. So we have a financing rate, and so risk affects our financing rate. Our CapEx, our capital expenditures for the plant, so our turbine costs and balance the system. Operational expenditures, which capture our sort of long-term reliability and need for component replacements and land leases and all that sort of stuff. And then that's divided by energy production, typically to get a cost per kilowatt hour. So that's the overall system level perspective. And so if we look at an innovation or a change to the plant design, we can't just look at it from an isolated perspective. Like if we think we have a new great blade design that reduces mass, it may also affect the loads, it may affect the energy performance and the reliability of the turbine. So innovations affect the whole system level and cost. So we want to look at things from a holistic perspective. And so that's what we do. That's the whole goal of our research at NREL. is to look at the wind plant from a holistic level, so an integrated system level performance and cost perspective of the wind plant. And so we have different objectives associated with this. We want to bring together our engineering and our cost models to be able to look at how innovation and design actually impacts LCOE. We apply a variety of advanced analysis methods to looking at analysis and optimization of wind farms. So multidisciplinary design analysis and optimization, MDAO, sometimes called MDO, is a suite of methodologies that kind of comes from aerospace, designing airplanes and things, complex systems where you have many different physical disciplines coupled together. So it's a great methodological space for looking at wind energy applications. And then using a common platform and tool set that can promote collaborative research. So everything we do is open source, everything's modular, so all the models sort of stand alone but can be coupled together. We bring them together to do wind plant and turbine design and analysis. So here's our tool set, Wisdom, Wind Plant Integrated System Design and Engineering Model. It looks big and large, but each of these models inside is its own models. So we have a tower model, rotor model, drivetrain, and all these stand alone or can be coupled together. So if you just want to do rotor analysis, you just use the rotor model. But if you want to do full turbine analysis, you can use the full rotor, drivetrain, tower model. We have models for the turbine costs, the plant costs. Again, these are individual models themselves that can be used together in isolation. Plant level models for doing energy production and financing as well. So you get the whole LCO perspective, and we can even couple these with our dynamic simulation tools like FAST if need be. But oftentimes we're just doing it with our quasi-static models. This capability is built on an open source tool set called OpenMDAO, which is Python based. How many of you use Python? Okay, I love Python. I'm a big advocate for Python. Down with MATLAB, up with Python. I know, sometimes that gets a pretty heated debate going, but so Python's open source programming language. If you know MATLAB, it's pretty easy to pick up. OpenMDAO is built in Python, so it builds on top of that framework, and it's meant to do multidisciplinary design analysis and optimization, so coupling many types of disciplines together and also different types of fidelities. So our basically tool set sits on top of this OpenMDAO environment. I won't speak about this today because that'll probably confuse things, but basically we have a standard way of connecting these models. We've collaborated with DTU Wind Energy on this, so it's more of an international collaboration on how to connect models together for wind energy system modeling. And how do we use this tool set? So we use it to look at integrated turbine design. So how can we improve turbine design if we look at things from a full turbine perspective, rotor, aerostructure, and the drivetrain, the tower. We look at integrated plant design for cost of energy, looking at things like plant controls and layout. We talked about layout and hub height, support structures for offshore, and even thinking about how can we do coupled design of the plant and the turbine. So site-specific turbine design. These are some areas that people are looking at. So bringing higher levels of coupling into the optimization process. What types of problems do we look at? So in optimization, I mentioned sort of gradient-based optimization. It makes optimization very computationally efficient. So you can do more and more complex optimization with more disciplines and things like that. So we do a lot of work on analytic gradients, using discrete decisions like discrete turbines, uncertainty, bringing uncertainty into the optimization so we can have more robust solutions to the optimization problem, multi-fidelity, and adjoints. So these are all different techniques we use. And I'm just going to use one example today. And this, I'll do this, and then I'll close out with a software demonstration, and then we're going to be done for the day. So hold on with me. We're nearly there. All right, so we talked about wake steering already a few times. We have a steady state model called Flores that we use to actually model energy production that takes into account the yaw control and the benefit you can get from wake steering in terms of deflecting the wakes away from downstream turbines. And so we've incorporated this into our optimization tool set so that we can look at the optimization of the controls of all the turbines as well as coupling that with layout design. So here's an example again of how you can get a power performance gain. This is in an LES simulation from using the wake steering in practice. So estimated 13% power improvement for that direction and speed. And so what we're going to look at here is we're going to take a plant. This is the Princess Amalia, which is an actual wind farm. You can go and get the statistics on the wind resource and the layout for these turbines. It's in Europe. It's an offshore wind farm in Europe, so Princess Amalia Wind Farm. And here's the layout of the actual turbines in the plant. And then you have basically a baseline power production. So this is already taking into account the windrows and showing the overall power production you get for this site for all the different directions. And so then we're going to look at comparing to this baseline, which is the existing layout and power production, optimizing the yaw settings for all the turbines in the park for every direction and wind speed it operates at, optimizing the location around. So if we were to optimize the layout of these turbines, could we get any benefit? And then both combining the optimization of the yaw control and the location together. So 3 different optimizations here. So here's the baseline compared to yaw optimized. So if we take for every direction and speed coming into the plant, accounting for the frequencies of those, the windrows, and optimize the yaw setting of each turbine in the plant, we get potentially a 5% AEP gain. And that can translate to hundreds of thousands of dollars, US dollars, in annual revenue for a relatively moderately sized wind plant. So that's a lot of money. Okay, so that's great. What if we were to actually re-optimize the plant? Let's say we're designing it new and we just want to get a better plant configuration in terms of the turbine settings. Position optimize, we can get about a 1.5% gain. Okay, so maybe there was some quirks and the turbines weren't placed well in the beginning. What benefit could we get? Now, what if we actually combine those together and actually optimize both the layout and the yaw? Okay, we can get the same benefit we did from just the yaw optimization, so what? Well, what's cool about this, though, is notice that the power density. So the power density is now 8.8 compared to 5.8 with the same increase in energy production. And what did we say before about spacing the turbines closer together? What goes down when you space turbines closer together? Infrastructure costs, right? All that electrical cabling and stuff. And so we went from a wind farm that was originally sized where the black line is to one that's sized where the red line is. We're reducing a lot of costs potentially in that park. So we can get energy gain, cost reduction, overall LCOE drop of 5–10%. So that's exciting. So that's our tool set. We do those types of optimization studies looking at how we can improve plant design. So what I'm going to do now is I just want to show you our software and how to access it. So in case you guys are interested in playing around with it, you guys can access it on your own time. So I'm going to switch over to this computer here somehow. Okay, she's got it. All right. Okay. So, okay, that's that. All right. So, all of our open source software is housed on GitHub. How many of you use GitHub? The Python people do, I'm sure you do. So GitHub is a repository for software, mostly open source, open access software. We house and keep all of our software on this website. You can use version control as you make new releases and things like that. So you can see all the different models associated with our tool set. And within this, Flores is one of the models. And this is our wake steering model. The one that I showed you just now in terms of that wake steering optimization example is Flores. So there's Flores SC and Flores. Flores is the one we're going to look at. And so you can actually download or clone it if you actually use GitHub to your own computer, install it. So again, I use Python, and I have information on this in the slide. So I recommend Conda if you're, to use Python. And then Jupyter notebooks are great. So all this stuff is gibberish to you if you don't use Python. But essentially, you download the software, you set up a Python environment, and then you can actually run the software. And it comes with a built-in tutorial. So it has the code inline. And so what this file actually steps you through is running a wind plant optimization. So it sets up Flores, it calculates the wake, and so then it'll show you, it's using just a simple 4-turbine example. It shows you sort of the wake deficit for each of the turbines as estimated by the Flores model. It does that both horizontally and vertically here. And then it walks you through actually doing an optimization with Wake Farm with that model. So in this case, it's just calculating the optimal yaw angles for a single direction and speed. But then it can actually calculate the overall energy production and then actually calculate the optimal yaw setting for all the turbines in all the directions. You can add to that layout variables as optimizers as well, play around with it yourself. It's a great tool set, and it's set up to be user-friendly so you can get some experience and play around with doing your own energy estimation processes or looking at more advanced kind of controls optimization studies. So that's available to you guys, and there's access information in the slides. So if you want to go through the slides or email me later about it, I'm happy to send you more resources. Okay, let me turn it back over to the slides now. Okay, I only have like 1 or 2 more slides left, so we're basically done. But let's just wait for the projector to come back up. Okay. All right. And then I have my clicker somewhere. There it is. All right. So that's kind of the software and how you access it, just in terms of where it resides. Not yet? Okay. Okay. Yeah. So that was that. So yeah, again, it's at this address, Flores. All of our software is there. And it's in Python, so I recommend Anaconda. If you haven't used Python before, it's really easy to pick up. And there's information in the README about how to install and use it all. But it's built with the Jupyter Notebook, so you can pick it up and run it pretty easily. If you know Python, it shouldn't be that hard to learn how to use. And if you don't know Python, you should learn Python. So, oh, it stopped working for me. Okay, yeah, so then just kind of finish up here, we have a number of open source tool sets out of NREL that are all available on GitHub now. So SOFA, which is our wind farm simulator that showed all those pretty visualizations earlier, our CFD tool set, that's available on GitHub. Wisdom, which is our optimization tool set, is available on GitHub. And then FAST, OpenFAST, is our aeroelastic and dynamic simulator tool, which also has now plant level dynamic modeling capability as well. So all of these are available on GitHub. You can download and use them anytime, and they're out there because we believe in sort of the open source approach to research in the wind energy space. That's been a tradition at NREL for a long time now. So I think that's it. I'm going to pause there. So in your slides, there are a number of more advanced optimization case studies if you're interested to go through. You can email me about them if you have questions at any time. And at this point, I'm happy to take any additional questions you may have.
This guy Arthur is watching you on TV, and he sent me an answer. So I'm making his answer. He would like to know if there is any kind of research on NREL about maintenance. Maintenance, wind turbine maintenance, yeah. Maintenance. Okay.
Yeah, so there's certainly a lot of research both at NREL and the larger community on what we generally call reliability and operations and maintenance. So there's a whole lot of research investigating different failure modes for different components of the turbines. So we have a gearbox reliability collaborative, a drivetrain reliability collaborative with industry, a blade reliability collaborative. And because of the complex loading of turbines, again, the complexity, the uncertainty in the physics, you have a lot of premature failures with the technology, and so understanding the root cause mechanisms of those failures is open-ended in many cases. So a big one right now is on bearings and this white edge cracking in bearings. So there's a lot of research going on trying to understand why they fail, how we can improve the models better to predict those failures. And then there's a huge growing area of research with respect, again, to the data science side of gathering and using all this data and physical modeling together to try and do better prognostics and diagnostics to better predict when things are going to fail, so we can create better strategies for when and how to fix things, and maybe how to change operation of the turbines to prevent failures. So that's a big research space overall, and NREL is definitely active in it.
Okay. So first of all, congratulations for the very good presentation. It was really interesting. And then I still have 2 questions. One regarding the yaw control. So from a developer point of view, it's awesome, perfect, because we will increase the energy generated. But have you already talked or already experimented using this kind of strategy with some wind turbine manufacturer? Because I'm not sure if they will be really happy with this.
So the short answer is yes. Some that I can speak publicly to and others that I can't. So we're working with both OEMs and owner-operators on wind plant controls generally and the wake steering with yaw controls specifically. So right now we've been doing a demonstration in a plant in Colorado with GE turbines with at NextEra, which is the biggest owner-operator of wind in the US, and been basically demonstrating the wake steering on a subset of their turbines. We've done that with other manufacturers as well. Some of those we can't disclose. We don't have conclusive results yet. We have some data in-house. That data in-house is very promising. It's showing that we're generally seeing the trends that we want to. Of course, field data is very messy, and so we're still working through the data analysis, but hoping to publish something later this year that actually shows the results of the actual wake steering in practice in commercial wind plants. From an OEM perspective, I would say that pretty much all the OEMs are also in-house actively looking at and developing sort of plant-level control technologies.
So my second question is a very general question. So I follow the reports from NREL from quite a long time, and I always wondered why NREL produces, just to understand how NREL works. So why NREL produces this kind of very good and very good quality reports and do not, let's say, produce a lot of papers, because one NREL reports could produce a lot of very good papers. So is NREL, let's say, yeah, it's a general question. So is NREL also publishing or making publications or making articles, or only reports? And why, if you only reports, why only reports?
So for the scientific research that we do, we typically publish in conference and journal articles just like everyone else. I mean, that's our main metric. And so there's a lot of, if you go to like, Wind Energy Science, Wind Energy, we publish all the time in those wind journals typically, torque conference papers, AIAA. For the market analysis type of work where we're doing like techno-economic analysis and cost analysis, historically those have been focused more on technical reports, because a lot of that work is very comprehensive and they're done as large reports for DOE, and they just don't fit well into journal papers a lot of the time, but we're starting to publish more of those as journal articles. But I think that our technical reports, because they're so comprehensive, that's almost why they're valuable sometimes. So sometimes it's nice to have that longer compendium. So oftentimes we'll do both. So yeah. I don't know who's next.
Hello.
Do we need to stop at any time? You can.
My name is Heitor from Brazil, and congratulations for the presentation. And I would like to know your opinion about the small wind turbine area. I've read many documents from NREL, some roadmaps, and I would like to know your opinion about that. I'm not sure if that's your area specifically.
It's not my area at all, which is why I didn't talk about it. But we do have people at NREL that do work on what we call distributed wind, which includes both medium-sized turbines or one-off turbines, as well as small-scale turbines. Yeah, so there's definitely people that do research at NREL in that space, and we're still active in it. I am not, but if you email me later, I can try to connect you with, you know, the folks in that area there. I can't speak intelligently at all about small wind.
So in your presentation, you talked about the risk of innovation, like that it occurred, and you had this factor that appeared in the LCOE, which was the FCR. How do you measure it? How do you choose this factor?
Yeah, so LCOE is what we use a lot actually at NREL, because DOE use that a lot to compare across technologies like solar and coal and natural gas and things like that. They often distill things down to that metric. And the nice thing is you can kind of assume away some of the financing aspects and just look at the technical aspects. You know, industry typically will use more sound financial metrics, so they'll use their net present value, NPV, their internal rate of return, IRR, to evaluate projects. Like I would say probably, and the developer again can speak, but I would say internally in industry, you almost never use LCOE to evaluate a project. You use NPV or IRR, or payback period, or those sorts of things. So it's more of like an academic metric, but it's one that we can use to compare across technologies and compare innovations easily without having to get into the complexity of the financial modeling.
But how do you account for risk in the investment?
Yeah, that's a good question. Not very well. So oftentimes, you know, we'll try to capture the effects on, say, reliability and things and bake that into the OpEx metric, but actually looking at how things impact your financing terms is something we sometimes use expert elicitation for, but we often can't really speak to too much. We have to evaluate mostly at a technical level. All right, well, thank you guys so much. It's been fun. And yeah.
Thank you. Thank you, Catherine, very much. Thank you, everybody. So I would like to say one last one. This was the last lecture. It was wonderful. Thank you very much, Catherine. And I also like to thank Professor Simões, who provided us the opportunity to gather together here. Such a great meeting, such a good school. So please clap Professor Simões as well.
Okay, actually we thank you all the three lecturers. Was really a great lecture. We really closed the school. I mean, the lecturing part was very, very good. And I appreciate your coming. Some came from Europe, from the United States, and here from Federal ABC, which is closer. But thank you very much for this opportunity. Some of you have been, of course, I have to tell all the team from the lab. Here we have please everyone, some are not here because too tired or doing something else. Who's from the CISEA? So we have here Luma, Lina, here we have Beethoven, and also we have the Julian's not here, and the secretary did a great job too, the Adrienne and Vanessa, yeah, Adrienne right there. So please give them a hand also. And well, before we finish today, some words about the poster. All of you have received the email I sent. And tomorrow, you are free. Some of you are being asking if you want to do somewhere else, in hotel or the shopping center, wherever. You can do in any place. You can work together at any place. We are going to reserve here this this place here for some of you who wants to come here. And also we have another place in the RCGI. There is another room there, and also you can work in the library. If someone doesn't have access to a computer, we have all set up in our lab 4 computers to get access to the internet. So those who are willing to work in this area, either here or the library or RCGI or my lab, come here at 9, okay? There will be people from the lab will be helping you to go to these areas. As I strongly recommend those who are finishing that send me as soon as possible tomorrow, just beginning of the afternoon if possible, so I send to print it out. Now, then on Friday morning, I need to receive at 8 at most. I'm gonna send to the place they're gonna print. Then you can get the poster. Right after lunch, or 1 p.m., something like that, you're gonna post this display then outside here, and then we're gonna have a system for you yourself to choose which ones are you like most, and then at 3 p.m. we're gonna close the school. Okay, all right. It has been so nice to have you all here. You support this almost now is 64 hours of intensive course, right? 64 hours. It has been great for you too. Hand for you too, okay? All right, so see you tomorrow.